Hello, thanks for watching this senior project presentation video. I'm Brendan DeClercq. Along with this presentation is Dan Crosby and Tyler Miller. We're excited to demonstrate what we've been working hard on over the past year. We've been designing an air-cooled polymer electrolyte membrane hydrogen fuel cell. And it's been a lot of work, and we're glad to show that to you today. So thank you for watching. So we set some objectives for this project at the start to keep ourselves on focus throughout the work that we were doing. Our main objective for this was to design an air-cooled fuel cell stack and really try and minimize weight with every step of the process. So to accomplish this, we had to do some calculations and simulations to determine what heat transfer requirements we had to overcome, as well as pressure drop requirements for our fans, so we could specify those to operate the cells. We also wanted to evaluate our performance of a single cell and redesign off that data. And then we also are going to design and build a program and control system for the stack so that it can do an automated operation without any user interface. And then our final objective for this project was to build a large-scale hydrogen test stand so that when we're completed with our full assembly of our fuel cell stack, we can put it on a test stand and evaluate our overall performance and compare it to what a typical fuel cell should get. So the operation of hydrogen fuel cells is pretty simple.
Before we designed the stack, a few fuel cell characteristics had to be taken into consideration. PEM fuel cells typically function at a correct pressure and a correct temperature. For our cell, we needed the temperature to be maintained around 60 degrees Celsius in order for the cells to function properly. Excessive temperatures will result in the cell not working and potentially melting important components of the stack and cells permanently. Our design is going to be cooled by a fan that will be pulling air through the cell instead of pushing it. And the fans will also be supplying the oxygen to the cell for the reaction. This design is also intended to be lightweight for applications such as flight, so the materials used will be lightweight metals where metals are necessary, such as aluminum, and our end plates are going to be made out of acrylic, whereas typical fuel cells end plates are made out of metal. In order to find a fan that we need, with the right specifications that we needed in order to cool the stack, as well as overcome the pressure differential across the cells, we needed to run a few calculations. The three results that we needed from these calculations were the outlet fluid temperature, the volumetric flow rate, and the pressure differential across the channels. Before we could run these calculations, we had to come up with a few assumptions. We assumed that the active area for each cell would be about 150 centimeters squared. The voltage from each cell would be about 0.6 volts, and the current from each cell would be about 0.8 amps per centimeter squared. Each channel in the cell would be about 1.8 millimeters in diameter. After running the calculations, we found that each cell would give off about 72 watts of heat. Multiply that by 10 for each cell in the stack, and we would have to remove 720 watts of heat. The volumetric flow needed to remove this would be about 216 CFM, and the pressure drop across the channels that we needed the fans to overcome was about 0.24 kPa, which is about 4.5 inches of water. After doing the calculations, we decided to run a few simulations to confirm our results. We ran a flow simulation through an individual cell, and we set the volumetric outlet volumetric flow to about 200 CFM, and we set an internal temperature of 90 degrees C. We also set the outlet pressure to be atmospheric. After running the simulations, we decided to do a few cut plots to see what was going on inside each cell. We found that the pressure drop across the cells was about 500 pascals, which was around the ballpark of where we were. The max temperature for the cells was 86 degrees C, which is beneath the melting point for the materials inside the cells. And it was also at certain parts of the cell. Uniformly throughout the cell, it was between 60 and 80. And we found that the air velocity through each channel was about 25 meters per second. Once we were able to obtain our results and the specifications that we needed from a fan, we were able to choose a fan. We ended up going with a fan from Delta Electronics that we purchased through DigiKey. The fan is able to supply 130 CFM, which isn't enough, but if we bought two of them and put them in parallel, it would provide about 260 CFM, which was more than we needed, which would end up helping more with the cooling. The static pressure from these fans was about 1.24 kPa, or 5 inches of water, which is more than what we needed. And to power these fans, they need about 12 volts DC with 4 amps and 100% duty cycle. These will be powered through lithium-ion batteries.
Everything inside of the cell needs to be extremely corrosive resistant and durable because this is such a harsh environment. So for our end plates, we chose acrylic because acrylic is a non-conductive, lightweight, easily machinable, and structurally durable to compression and corrosion. As for the rails on the outside of the cell, they're only to compress the end plates. So we chose aluminum because it's lightweight and inexpensive. Our current collectors are one of the most important parts of the cell because this is where our output is actually taken from the cell and applied. So we used copper because copper is extremely conductive. Stainless steel was chosen for our corrugated channels and foil because stainless steel is extremely corrosive resistant and is a good conductor as well. Su Quang is a thick adhesive which seals well. This is why this was chosen as our gasket material. As for our spacers, we chose Delrin because Delrin is a polymer, which polymers are low conductors and they're resistant to heat, corrosion, and are structurally stable. Our gas diffusion layer is one of the most important parts of the cell. So we chose a material that was hydrophilic, which allows passage of heat and water removal. So we chose carbon papers as our diffusion media. Lastly, our membrane has to be a semi-permeable material, allowing the flow of protons while keeping gas and hydrogen out. So we chose a strong ionomer as our membrane layer. All of the components used to create our stack were actually made using tools available to us by our Alfred State Machine Shop and labs available in the Mechanical Engineering Building. Some of the equipment that we used was a Next Wave Automation CNC Shark automated router mill for our end plates, a machine shop bandsaw and drill press for our aluminum rails, a sheet metal corrugator for our corrugated stainless steel channels, a Epilog Laser Fusion M2, which is a laser cutter used to cut our frames and our spacers. And lastly, for various components such as our fan shroud and different prototypes we made, we used a MakerGear M2 3D printer. So to create our stack, we actually needed to make several sub-assemblies first. At the very bottom, we have your dry end assembly, which is a copper rod, dry end plate, and current collectors fastened together. Above this, you have your cell frame, which is a cathode-sized diffusion media, corrugated stainless steel channels, anode foil, anode frame, and an anode diffusion media with channels cut into it for gas flow. Above this, you have your membrane electrode assembly, which involves an anode catalyst, your membrane, and your cathode catalyst. Above this, you have an end cell, which will stay with the stack the entire time you're using it. This is an anode foil, anode diffusion media, another anode diffusion media, anode frame, then foil, then a cathode diffusion media. Then finally, to top it off, you have your wet end assembly, which is a current collector, wet end plate, and copper rods, which all of this is fastened together using various bolts and screws. Now to add more cells to the stack, all you need to do is put another cell frame and membrane electrode assembly inside of your stack.
So along with this project, we designed a control system for the stack. Shown here is our power conversion box. We're going to convert the 6-volt DC input at around 80 amps to 100 amps depending on our performance, and then we're going to change that to 120 volts AC, and we do that through these 6 to 12 volt DC converters, and then we take the 12 volt output from that and we power a power inverter and get 120 volts AC out of it, which can power most household appliances. Along with this control system, we have a automated stack management system. We used an Arduino Mega 2560 to control this stack. So some sub-programs that we have in here, we have temperature management, where if the cells get above 70 degrees Celsius, we're going to increase the pulse width modulation duty cycle to 100%. So it's normally going to be around 50% to keep overall power consumption down. But if the temperature gets too high, we're going to have to increase the fan speed to provide more cooling. We also have a voltage monitoring system that when the hydrogen gas gets used up, the overall voltage is going to drop across all the cells. So when it gets below our set 5 volts, we're going to depressurize the cells, which is going to let out mainly nitrogen because the hydrogen is going to be used up. And then we're going to let more hydrogen gas in and repressurize the cell and increase the voltage. Another subprogram we have is our emergency stop system. So if any cell gets below 0.4 volts, we're going to disconnect the load and depressurize the entire stack so that we don't make one of our cells go negative and eat itself. We also have the test stand design that we've been doing in this project. Some major components of this test stand are the National Instruments SCXI 1001 chassis. This is our main brain of our system. It's a data acquisition system that can hold up to 12 modules. We're using 5 modules into it, so we're able to read thermocouples, analog inputs. We're able to output analog signals, and we're also able to output digital signals, and there's also a high voltage relay switching board. Another main component of this test stand is a recirculating bath, and we use that to heat up a large scale stack. Not our stack, our stack won't need this, but some large scale stacks that might go on this test stand in the future will need to be warmed up before they run. So that's why that's there. We are going to communicate through RS-232 in LabVIEW to control the recirculating bath. We also have a 5 kilowatt humidifier. We have 2 of these humidifiers from the fuel cell store to provide humidification to the anode and cathode, or the hydrogen and oxygen systems. And one of the biggest components of this test stand is the Dynaload XBL series load bank. We communicate to this load bank with a GPIB bus and LabVIEW. So this load bank will provide a variable resistive load across the cells, so we can get up to 6 kilowatts of power through this load bank.
On the test stand, there were a few components that needed to be calibrated, such as pressure transducers and flow controllers. We were able to calibrate these using LabVIEW, and we would set up a VI for each component. For the flow controllers, we would incrementally increase the voltage, and we would compare that to a known reading of flow through the flow controller. For the pressure transducers, we incrementally increased the pressure, and were able to compare that to the voltage reading we were getting from the transducers. Thankfully for us, every component on the stand, the calibration for them was linear, so it was very easy to calibrate. Also for the test stand, we had to set up the electrical box. The electrical box was important because it controlled how the power was distributed throughout the stand. The three-phase power would come in from the building, and it would go through the box through a number of safety features, including circuit breakers and fuses, and then it would go through a few outlets. It would go to an outlet on the side of the box, and then up to a quad box that would also distribute the power, and then to the heaters on the stand. Once the power leaves the electrical box and goes to the quad box, it is then sent to the top of the test stand. At the top of the test stand, the 120 volts DC, neutral goes into terminal block 5, ground into terminal block 6, and hot into the fuses. Once going through terminal blocks 5, 6, and the fuses, it is sent to the transformers. In the transformers, the 120 volts DC is converted to AC by going through the transformers and then a full bridge rectifier in each of the 3 transformers. The first transformer converts the voltage from 120 volts DC into 5 volts AC. The second, 15 volts, converts to 15 volts AC, and the third to 24 volts AC. Transformer number 1, the 5 volt AC, sends signals to the solid state relays, which activates the heaters. Transformer number 2, the 15 volt transformer, signals the flow controllers, and transformer number 3, the 24 volt transformer, can send signals to the pressure transducers.
Our design for a lightweight hydrogen fuel cell is desirable because of its higher energy per mass and volume ratio that you can't get from a lithium-ion battery or other heavier mobile power devices. One of the applications we talked about was a mobile or small home that could be powered typically between 1 kilowatt or 20 kilowatts. Another application would be drones or other military surveillance equipment. This equipment needs to be run at a high power output with a lightweight supply that will last for a long duration. That's why our design for a lightweight hydrogen stack would work well in these applications. Looking forward, we will continue our research to complete a fully functional hydrogen fuel cell. Some of our components will have to be redesigned to better hold pressure under various conditions. When the cell is complete, we would like to obtain data on its performance. And lastly, we will assemble the completed 10-cell stack and test its performance on our large-scale hydrogen fuel cell test stand. So to summarize our project, we've designed an air-cooled hydrogen fuel cell stack. We've sourced all of our required hardware and components to build the stack. We've assembled a single cell to determine its functionality. We've programmed and set up a control system for the completed stack to be tested. We've designed and built a full-scale hydrogen fuel cell test stand. And currently we are redesigning and debugging a single cell before we can test the full capabilities of our design of an air-cooled hydrogen fuel cell stack. This project was also made possible due to the support group that we've had along the way. We'd like to make special acknowledgments to Plug Power for the catalyst-coated diffusion media, to Paragon Steel Dies for the dies to manufacture most of our components, for Nowagen for support in building the test stand, Alfred State College, faculty and facilities, and Dr. John Owegian for being our project advisor. Thank you all.